Hello everyone. For my heat transfer project, I chose to construct a transient conduction calculator. A little bit about transient conduction. It was developed to determine the time dependence of a temperature distribution for a solid during the transient process, of course, as well as determining heat transfer between the solid and its surroundings. For example, temperature gradients within the solid can be neglected if you know different properties of the material. This approach comparatively was called the lump capacitance method and was used to determine the variation of temperature with time, heretofore known as dt over dt in our class. If a more complicated method is need to be used, then it's termed one-term solution. So a little bit about transient conduction is the history is they wanted to solve through lump capacitance. An example is considering a hot metal forging is initially at uniform temperature and is quenched by immersing it in a liquid of lower temperature. So here you have a piece of hot molten metal and you dip it in the liquid, and as you can see here there is a boundary condition and the energy of the liquid is going out into of the metal is going out into the liquid, which is over here. And this is a little bit of a lump capacitance problem, as we can figure out the temperature of the molten metal, the temperature of the surrounding liquid, which would be T infinity, and since that T infinity is less than the initial temperature of the metal, we can determine the time it would take for the liquid metal to cool. The primary focus of transient conduction is it's noticed by its bio number and its Fourier number. The bio number is a ratio of thermal resistances. The definition from the book is located here. This graphic here, figure 5.4 in the textbook, in the 6th edition of Fundamentals of Heat Transfer and Mass, we see different bio numbers through the same material. So here is a material and it's being transiently cooled. You have airflow on this side and airflow on this side, and we can see the distribution of heat as it goes through the different bio numbers. The bio number is a ratio of the resistances, and so as the number is changed, you can see the graphic differences of its relationship. So a little bit about my calculator. How it works is through this flow chart we can kind of get an idea how it works. Since everything revolves around the bio number, it says we need to calculate that first. So my bio number is, as you know, is you need your heat transfer coefficient, your effective length of the surface in which you're going over, and your K value of the fluid that is passing over the object. And so with the bio number, it'll go through and spit out a bio number, and then if it is less than 0.1, it'll say, hey, it'll show up the text, you have a lump capacitance problem, and it'll provide you the bio number. And if you're doing lump capacitance type problem, it'll ask you for the known inputs, and then it'll ask you for what variable you're solving for with the equations from our equation sheet. And so it'll say, oh, you know, it says, oh, what do you want to solve for? dt dt, c sub p. It'll come from this pool of equations here to determine exactly what it's looking for. Otherwise, it'll say, oh, the bio number is greater than 0.1. Okay, so then I need a new bio number, and then based on the geometry, if it's an infinite plane, cylinder, or a sphere, it'll then interpolate your zeta 1, c1 values, and then it'll go to a solve, and what it does is it solves for this theta star naught, which is a non-dimensional group, and the way I set it up is that it actually converts the one-term solution into this value first before solving for the Q, your heat ratios, your temperatures, or your time for your respective geometries. And so it pulls all those values in. What it does is it solves this value first. So let's go through a couple of examples. The first example we'll go through is found on day 19, the non-text problem. And so plugging my the numbers into the calculator, It asks first for the heat transfer coefficient, the effective length, and the K of the fluid. Now these are things that the user is going to have to infer from context and know for themselves. It'll then create the bio number, and it'll see the bio number is less than 0.1. And so then it's like, oh, it's a lump capacitance problem. And it's like, okay, well then we'll use the same bio number. And then it goes to the equations and it pulls information that is asked for information to be provided. And you enter in the temperature, the initial temperature, temperature infinity, and the species of P, surface area. That's up. That geometry is going to be something that you have to solve for individually. And then it just plugs all the information into the calculator, and it comes out to be 290.034 seconds. And to double check that, here is my homework of the same problem. So I didn't carry it out to exactly this far many decimal points, and the surface area is calculated, and so we can see, yes, it works. So let's try a different example. A little more different example is going to be our day 20, problem 5.2 from the heat transfer textbook. This is the 6th edition. And so reading through the problem, we do it again, we plug in the values. It says it's a one term, calculate a new bio number, interpolates, and then what it does is we're given this value, and so it solves for everything in theta star naught. And since these values are inputted as alpha into the Fourier number, then it comes back and it gives us the time. Now there's the part B to this problem, and this part B is more of an iterative problem, but one of the things I learned through calculating through the homework is this part B is its energy storage is equal to energy stored. So we do m dot c sub p dt over dt is equal to the same, but then we have this 0.2. So our equation looks kind of like this, but with a simple algebra it looks like this. So I'm wondering if then we can then do that, and from our equation sheet it looks really close to this equation here, this theta star naught dimensionless value. And so I was trying to figure out how to do that, and I wasn't able to do that. Now depending on the geometry of a cylinder, sphere, or any specific point you want, it'll solve for that. The code had some challenges to initially type it in. There's a lot of tediousness of typing in values from table 5.1, but other than that, that was what I chose to do for my heat transfer project, and I hope you enjoyed it. Hope you learned something. Thanks, and bye.